Okay, so today's lecture will consist of understanding and proving Ramachandran's model. So let's first introduce who is Dr. Ramachandran. So he was a physicist who worked on peptide structures, and he was the first to propose the triple helical model for the collagen. Okay, so he almost won a Nobel Prize, but I think he lost to Linus Pauling, who discovered the double helical structures of some of the proteins. Okay. He made significant contribution to discovering this something called Ramachandran plot, which is still used to this date in understanding protein structures, predicting protein structures, and so on. Okay. So to understand Ramachandran plot, what we have to first acknowledge that there are certain restricted bond rotations in the Ramachandran plot. Okay. So what, for example, in a peptide structure. For example, this is the peptide here, right here. This is the peptide. So this bond, this part is part of one amino acid, okay, and this part is the part of the another amino acid, okay, and they are connected together by this peptide bond. So what happens here? This N has a lone pair, which then participates in conjugation and then creates this plus and minus charge here. So what happens is this particular bond, this peptide bond, has something called a restricted rotation. Okay, so restricted rotation. So restricted rotation means this is difficult to rotate, or it will not be rotating like a single bond. As opposed to this bond will have a free rotation. This bond will have a free rotation, but this bond, because of this double bond character, will not be rotating. So this leads to some restriction in the overall protein structure. So what are those? So for example, let's say this is a protein backbone. Okay, so this part here, C alpha CO, this is part of one amino acid. Okay, so this is AA1, for example. This is the N-terminal one. Okay, then this is another one. So NC alpha CO. Okay, carbonyl. So this is another protein. Okay, so this is, let's say, amino acid 2. Then this is followed by another N, C alpha C double bond O. So this is amino acid 3, and so on. Now, if you look at the peptide bond that connects these three amino acids, this is one peptide bond right here, okay, which connects this to amino acid, okay, and this to amino acid is connected by this peptide bond. Now, what happens here is that this bond has a restricted rotation, as we discussed here. So this nitrogen, carbon, oxygen, and hydrogen, they have a restricted rotation, and they do not really participate in any bond rotation, because this is a double bond character of this particular bond. So this bond do not rotate, but anything surround it, for example, this bond, this rotates. This bond after this rotates, but this does not rotate. Similarly, the next bond next to it rotates. The bond after this rotates, but this bond do not rotate. Okay, so there are some similar restricted bonds which do not rotate throughout the protein backbone. Okay, this do not rotate as a part of the peptide bond. This do not rotate. That's a part of the peptide bond. Okay, the peptide bond. So like that. So depending on this, you can predict that some of the this will impact how the protein structure overall. So we will look at how these two bonds, so this particular bond rotation and this particular bond rotation, they impact the structure of amino acid and as an overall protein structure. So this is what Dr. Ramachandran's contribution is. So he discovered this first, and he figured out that this would have an overall contribution in the protein structure. Okay, so this structure, if you zoom in a little bit, so we will look at the functionality of these two angles. So phi and psi. Okay, so phi being the angle between C alpha and the adjoining nitrogen, that is the N alpha of the amino group, and psi being the angle between the bond connecting the C alpha and the carbonyl. Okay, so this is carbonyl, right? So this is a carbonyl. Okay, so this is the NH2. Okay, this is NH2. Another H is hidden, so that is that. Okay, so again, phi, the rotating bond angle, or we call it dihedral angle. I'll explain that in a moment. Bond angle between C alpha and N alpha, and psi is the bond angle between C alpha and carbonyl COOH. Okay, that is the I would not say COOH anymore, so I'll say just C double bond O. Okay, so that is probably a better way to represent this because there is no more COOH here. Okay, so that is what we are going to explore in a moment. Okay, what exactly Dr. Ramachandran did. So in a theoretical qualitative model. Okay, so what he figured out is that so once you rotate this angle, so he plotted the energy of the these two bond angle rotation with each other, and found that some of them would be restricted. So what are these angles? So these two angles are called dihedral angle. Dihedral means, the term dihedral means between two planes. What are the planes here? So you are probably familiar with a normal bond angle. So this is a methane bond angle. So this is a normal bond angle. So dihedral angle means, if you, let's say, consider that this particular part of the molecule is one plane, and this particular part of the molecule is another plane. So this angle signifies the bond angle, or the angle between these two. Okay, so whenever these two rotates, there will be some angle generated with these two. So okay, that angle is called phi. Okay, similarly for the psi, I'll use a different color. For the psi, the dihedral angle will consist of this part. It's not a very good color. This part of the bond, this part of the as a plane, and this part as a plane. Okay, so whenever there is a change in the angle between the, that is the change in the psi. Okay, so that is how the dihedral angle is considered between the two. Okay, so if we clean up the structure slightly, and let me duplicate this slide a little bit, okay, just to have a better view. Okay, so you would see that some bond angles here, some dihedral angles here, for example, when the phi is 0 degree and the psi is 0 degree, so that leads to this kind of steric clash. Okay, and that would not be permitted. So what Dr. Ramachandran did, he measured what are the probable angles where there would be steric clash and where there would not be. Where there would not be, so steric clash leads to destabilization. Okay, so steric clash leads to destabilization, like it is happening right here in this particular picture. So that would be a high energy, so that would not be permitted. So destabilization is not permitted. So this particular picture, you can see this part here, in this part here, there is no structure. So blue means there is some structures, and there is no structure right here. Okay. Similarly, when the bond angle is, or sorry, the dihedral angle, when the phi is, so this part is 0 to minus 80. So this is minus 120, this is plus 120. When the phi is minus 120 to 180, and the psi is plus 120 to 180, that is this part, that part would be very stable. So there will be a lot of structures over there. Okay, so some stabilization over here, but no stabilization here. Some stabilization, a little island of stabilization here, but no stabilization here. Okay, So we'll prove this qualitatively, that how this is working using Avogadro model. It basically what Dr. Ramachandran did, he plotted the angle of psi with the phi and figured out at what position there is steric clash. Okay, and steric clash means destabilization. So those conformation would not be permitted. Okay, so that is his contribution here. Okay, so this is one example here, that this particular one is a area where this kind of very destabilizing steric clash is occurring. So there would not be any structure that is permitted. So the known structures that we know: anti-parallel beta sheets, parallel beta sheets, collagen triple helix, right twisted beta sheets. So all these structures are within this large area where there is a good degree of stabilization. Left-handed alpha helix is right here. Right-handed alpha helix is right in this other island of stabilization. Okay, and that's pretty much it. Okay, so the other structures are not really permitted. Okay, so let's just do a qualitative understanding of this, or how this is working. So to understand this, I have created a, so this is how we would do it. So you can try this yourself. Okay, so this is a tripeptide. So you remember, when we are understanding this, we need to take into account a tripeptide, because the alpha, C alpha or CO from the adjoining one, C alpha from the one amino acid, and the C alpha CN from the third amino acid has to be taken into account. So we need 3 amino acids here. So I have taken an amino acid. This is alanine, then glutamic acid, and then methionine. Okay, so this is the angle that would need to be considered. So C alpha to N, remember that is phi, and C alpha to CO of that amino acid, it's the psi. Okay, so this is what I written all here also. The C alpha to N, so C alpha to N is the phi, and C alpha to carbonyl is the psi. Okay, so that is what we will measure. Okay, so we will look at in Avogadro model and see that what are the relative energy for various angles that are written here. So that I have written these 4 quadrants as A, B, C, and D. Okay, so we will measure the relative energy in each of these quadrants. Okay, and then we will write them down, and we'll see if the model is correct or not. Okay, so to do this, we need to do something in this. That is, I will first, how do you label this if you want to do this yourself? Okay, so how do you measure the dihedral angle in the Avogadro? So if you want to measure the psi, you have to take the C-terminal amino acid carbons alpha nitrogen as 1. That is this one as the 1. Okay, then the carbonyl carbon as 2. That is this one as 2. This alpha carbon as 3. Okay, so this is your 3, and alpha amine as 4. So this is 4. Okay, so if you do this in the Avogadro, this will create the dihedral angle psi. Okay, and you can rotate this like we have done this before. Okay, so that will create the psi. How to make the phi? So to make the phi, I'll just tell you what the numbering scheme is. So for the phi, the N-terminal amino acids carbonyl carbon is 1. That is, this one should be 1. Alpha amine should be 2. Okay, alpha carbon as 3, and carbonyl carbon should be 4. Okay, so that should measure the phi. So let's just understand before we go into and measure this, how this is happening. So this is a peptide bond here, right? So this is a peptide bond here, meaning this part is part of one plane or a rigid structure. Okay, 3 and 4. So 3 and 4 right now, if you draw them in one plane, the angle between them is the phi. Okay, so this is the same thing what we did in the other slide. Okay, so now if you want to measure the psi, so let me just duplicate this for the easy understanding. Okay, delete the drawing. So let me go to full screen and see what is happening here. Let me choose a different color. Okay, that is red. So remember how I did the numbering. So this nitrogen as 1, carbonyl as 2, alpha carbon as 3, and this one is 4. So why what justification is this bond, the peptide bond, always has to be one structure, and then this part is the other plane. Okay, so the angle between them is the psi, right? So that is what we did here, the phi and the psi. Okay, so that is how we measured the angle. Okay, so this is psi, and the previous slide we explored the phi. Now let's measure it in the Avogadro. Okay, so and see if it is holding it or not. So to do this, I have done one more simplification so that it does not look very complicated. So what I have done, so see the adjoining structures and adjoining structures, that is this side chain, this does not really play a role in the phi and psi. I mean they do, but not for the what we are trying to do right now. So what I have done, this part and this part I have removed, and I will also remove the side chain of this carbon. Okay, so I will make this simple. So this part will be gone, this part will be taken out, this part will be deleted. All I'll be left with the main backbone and nothing else. Okay, and then that will help me show you the structure in a simpler manner without all the side chains. So the side chains do have a role, but let's come to that in a moment. First, understand the basic Ramachandran diagram. Okay, so let's go to the Ramachandran diagram. So I have created the peptide right here. Okay, so here this part is the alanine. So you can see the side chain CH3 right here. Okay, this is the N terminal, this is the alpha carbon, this is the CO. So we should delete everything that is right here. So what I will do, sorry. So I'll quickly select this part and delete. Okay, so I want to create only this part. Okay, this is the second amino acid, C alpha alphamine carbonyl. I want to delete the side chain. Okay, I want to delete the side chain. So I will delete this part, and maybe I'll keep it this part to keep it simple. Okay, this is the third amino acid. So this is the alpha amino, alpha carbon. Okay, and this is the carbonyl. This is the C double bond O, and this is the side chain. So I don't want to do anything with the a side chain, so I will remove the side chain. Okay, I don't need to do anything with this part also, so I'll remove it. Okay, all the hydrogens should be gone, and this is the part that should be remaining. Let me see if I can simplify this any further. So the CONH, this is still the NH I need, so I can also remove this part. Okay, so that is that. You can see that some structure has become much simpler. Okay, so let's see what is the phi and what is the psi. So if I zoom in slightly, okay, so this is the alpha carbon, this is the CN. So this angle, the dihedral angle that should come out of here should be phi, and this is the alpha carbon, this is the carbonyl. So dihedral angle that should come out of this is the psi. Okay, now let's do it. So we have to label them as we said. So let's first measure the alpha, the psi, that is alpha nitrogen as 1, and so we'll start from here. 1, 2, 3 and 4. Okay, so this gives the dihedral angle right here. Okay, so first thing we will do, we will try to fill up this box. We'll keep the psi at plus 120 to plus 180 degrees. So we want to get it to this part. So plus 120 to 180 degree, that should be this region, at minus 120 to minus 180. So if you look at this, so that is this region what we are talking about, this part. So we should have a good degree of stabilization, right? So let's get there. So I have let's decrease this slightly. So this is already at 158 degree. So it is within that region already. Let's check with this part, this angle. Okay, so how I do it? So I would need to start from the labeling from this carbonyl carbon. So 1, 2, 3, 4, and you can see this is minus 160, and you can see that is already measuring the dihedral angle as minus 160. Right, so this is minus 160 and this is between plus 120 and 160. So we want to measure the energy. So you can go to extension, molecular mechanics, and calculate the energy. Okay, so for some reason it is not doing it. Okay, let's optimize this slightly.